So going over chemistry, here's where we're at in terms of the unit. We're going to start by looking at atoms, how they come together to make your molecules. Molecules are then going to lead into the next topic that we'll get to, which is the macromolecules, the big molecules. And finally, this is going to reconnect back to where we started with the different organelles. 4 topics in this unit. All of them are below the level of organelle, so we're staying tiny here. Start out with general chemistry, that's just today. Go into water, that's just tomorrow for the most part. We're not going to spend too much time on water. Carbon chemistry into next week, and then chemical reactions. Those chemical reaction pieces, we're going to lay the foundation for it today, then come back to it at the end, okay? For all of this, if you're feeling like you understand it really well now, you're going to make your life easier down the road. But we're going to keep circling back and circling back, so you're going to have a lot of opportunities to make sure you're solid, which also means the sooner you're getting it, the better off you are going to be. So hopefully by the end of today, you know the parts of the atom. Hopefully by the beginning of today you did, but if not, by the end you will. What each part's doing, and more importantly, each of those parts, what their role is in chemical bonding. Because in biology, that's what we care about, are the chemical bonds and the chemical changes that happen throughout a chemical reaction, which is kind of the fourth piece of all of this. Okay, so we're going to look at matter and energy. Starting with matter, we can give it a nice fancy schmancy definition. Anything that has mass and takes up space. Matter is the elements. Let's make this easy. Matter, let's give me a pen, there we go, is the stuff. If you can hold it, it's matter. What are some of the elements? There's like a whole periodic table of them or something.
Oh.
Yeah, carbon, nitrogen, oxygen. That's matter. All of those different elements, which are just a whole bunch of atoms, that's all matter, okay? And so when we're looking at matter, we know that matter is made out of different elements, which is just a whole bunch of atoms, and atoms are made out of 3 parts: protons, neutrons, and electrons.
Yeah.
Whoop, whoop. So hopefully you guys know this by now. If not, we'll make sure to get there. 2 parts of an atom. What are the 2 parts to the atom?
The nucleus thingy and then that outside circle thing with the electron cloud.
Okay, I don't care if you call this the electron cloud, the orbitals, the shells, whatever. So long as you understand that the nucleus is the stuff in the middle, and then it's surrounded by these electrons. And more importantly, realize that this is not the same as the nucleus of a cell. Again, we are on totally different size scales here. It's like the difference between the size of an ant and Earth. So they're a little different. In this case, in an atom, the nucleus has the protons and neutrons. All familiar so far? These protons and neutrons each have mass. And remember we said matter is anything that has mass and takes up space. So even though right here I'm saying that the electrons have 0 mass, that's not entirely true. It's just so small compared to the mass of the protons and the neutrons that we're essentially like, 0-ish, okay? We should remember that when we're talking protons, we're talking a positive charge, electrons, a negative charge, neutrons are neutral. Okay. So we can start by looking at something like carbon. In its neutral state, it's going to have 6 protons, 6 neutrons, 6 electrons. Familiar so far? Okay. And what makes carbon carbon is the fact that it has 6 protons. Every single time you have an atom that has 6 protons, it is carbon. And every single carbon has 6 protons. That same relationship can be said between oxygen and 8 protons, etc. So the number of protons defines what element you're looking at. So when it comes to elements, there are 6 of them that are very, very common in the body, although this entire list you'll want to know. So the 4 most common are CHON, carbon, hydrogen, oxygen, nitrogen. We add in phosphorus and sulfur because they're in quite a few things as well to make chomps. And then the rest of these guys are in trace amounts. I wouldn't expect you to memorize this list. I would definitely make sure that you know if I write down Na, that that's sodium. If I write down Fe, that that's iron. But CHON, most common. CHOMPS, also pretty darn common. So carbon, hydrogen, oxygen, nitrogen are the biggest ones. Phosphorus and sulfur pretty important as well. Yay? Okay, sweet. Moving on to neutrons. This is why I love biology. You know what you need to know about neutrons? Something about isotopes. Maybe. If you want to go into nuclear medicine, you'll care about isotopes because some of them can be radioactive. As far as our purposes, neutrons have a mass. Moving on. Easy, right? Okay. Now's the part that I actually care about. As a biologist, it all comes down to the electrons. Because electrons have a certain configuration that if they don't have that right configuration, it makes the whole atom sad. An atom's well-being, an atom's mental state comes down to its electrons. So relatable, right? So these electrons are going to be negatively charged. They're chilling out in the electron cloud, and there's some rules to make a happy atom. We're going to always fill from the inside out. How many electrons can fit in the first shell or orbital? 2. How many after that?
4.
8 in the second shell. How many in the third shell? 8. How many in the fourth shell? Nobody cares because it's biology and all we worry about are the chomps, which all come before those fourth shells. So yay, keeping it simple. 2 in the first, 8 in the second, 8 in the third. Nobody cares about the rest. Okay?
So if it's on the
Is it
test,
16:30?
what's the one after 2, 3? After 30?
If it's on the test, it doesn't exist. Right? Biologists straight up don't care about anything that low on the periodic table because they act weird because they're metals, so nobody cares what they have in terms of their electrons.
So if that's not we're on the test, we say no one cares.
Yeah.
All right.
Fourth electron orbital, no one cares. Well, biologists don't care, and biologists are the only ones that matter, so yeah, no one cares. Moving on.
All right.
Are we okay with chemistry brought to you by this version right here? I like it. You are an atom, and you are not chilling with a nice full valence shell, meaning the outermost shell that you have. You're a sad atom, and nobody needs that in their life. So how do we happy you up? There's some...
This version is all right.
Okay, so 2 options. If you have 1 electron in your outermost shell, we can get rid of it. You can give it away. When you give away that outside electron, that means your next shell is full. So your valence shell is full. You become a happy atom because your valence shell is full. But that doesn't mean that you're not going to have the same amount of protons and neutrons. That's okay. If you lose, protons and electrons. Hello, brain. If you lose 1 electron, you're going to end up having more protons than you do electrons. That means overall you're going to have a positive charge. Remember that cations have a positive charge. Yeah, you knew it had to happen. Also, not to call anyone out.
Yeah. 8 is great, yeah.
If we flip that over to the other way, if your outer if your outer shell, as an atom, is missing 1 electron, meaning it's got 7, or in the case of hydrogen, it's got 1 and wants to get to 2 to be stable. So that outermost shell is just shy by 1. You can pick up an extra electron. Easy enough. That's going to give you 1 more electron than you have protons. That's going to make you a negative ion, which is your anion. And what do we all know about positive and negative charges? That opposites. Whoa, amazing. So the attraction of positive and negative ions is what is going to cause ionic bonds. So here we go. We got sodium. And he's sodium sad. And then thank you.
I like that one. It's actually pretty good.
Ah. Why?
I thought it was funny.
Yeah,
Oh, it was
right?
funny.
It's funny. And fluorine. Oh, wait, no, he said too. Just kidding. His mouth is detached. We've all been there. Let's put this back together. This one's dead. So fluorine is also fluorine sad. It was
I-
funny.
I'll let-
Get it?
I'll-
Fluorine. Okay. Thank you. So in this case, we've got a sodium. It's sad. Fluorine's sad for opposite reasons. One has one extra, one has one fewer. Easy solution here. We take this guy, we do a little yoink, put it here, and now what we've got is sodium that has more protons than electrons. It's not neutral, but it's stable, and so it's happy. That's going to make this little sodium right here a little bit positive. That's a positive ion, also called a cation.
Also known as a
Positive ion.
One job.
Cation. It's a cation. On the on the fluorine side, we're going to have more electrons, and we know positive, negative, those attract. So our cation, our anion attract to each other. What kind of bond is this?
ionic.
Okay, bond. Ionic bond. It's never going to get old. All right. But if you're carbon, your story is a little bit different. Carbon has 6 protons, 6 electrons. 2 in the first shell, 4 in the second, which means to form an ionic bond, carbon would either need to lose 4 or gain 4. Not super likely, right? Alternatively, it can share. That was fine. Okay. So in the case of carbon, here we go. We've got 4 valence electrons, 4 electrons in this outermost shell. Rather than gain or lose 4, very, very sad carbon can hang out with some very, very sad hydrogens
Misery loves company.
because misery loves company. But you know what? Then they all end up happy because they start to share
Group
these
therapy.
electrons. So group therapy is working out great for these guys. I don't know what kind of smile that is. Just creepy ones.
Surprise.
Shut. Oh, this guy's just straight up like, yay, it's happy time.
More eyes.
So in this case, the carbon is kind of temporarily borrowing 1 electron from each of the hydrogens, and what you're left with is a carbon with 8 valence electrons, and each of the hydrogens has 2. They're happy. Life's good, because remember that hydrogen only needs 2 because it's only got 1 electron. So it's at the lowest shell.
That's a molecule.
Boom. We done made a molecule. Isn't that pretty? Okay.
It's so happy.
If you can remember this chart right here, you're going to be in really good shape. Rather than spending all the time looking at the periodic table, figuring out, okay, 2 electrons in the first, 8 in the second, no. Remember this to make your life easier. Carbon makes 4 bonds. Hydrogen makes 1, oxygen 2, nitrogen 3. Why did I put those ones up first? Because carbon, hydrogen, oxygen, nitrogen, those are the ones that make up most of your bodies. That Sean right there. Phosphorus and sulfur get a little bit weird. So like 4 or 5-ish, 2 or 6
How do
is,
you do 4 or
yeah,
5? How do you do 5?
fun, for fun.
Are they magical?
And yeah, instead of having 8 in the valence shell, it still has 8 in the valence shell, but then kind of gives them away.
But not really.
But kind of, yeah, exactly.
He's a slime dog.
So if you guys can just really make sure that you know these, this is going to be a cakewalk.
I hate things. What's energy?
Good question. So if we're looking at energy now, the biggest mistake that people make is thinking that matter and energy are some kind of interchangeable things. They are not. Matter is what? One word.
Atoms.
Stuff. Matter is the stuff.
Stuff.
When we look at energy, by the way, what does this stand for up here? Energy. When we look at energy, we're looking at the ability to do work or to move matter. In other words, if matter is stuff, energy is the ability to move stuff. Okay? So the types of energy that we're mainly going to look at is energy that is actively being used or energy that is being stored that can be transformed into a type that can actively be used. In other words, energy of motion, this is this. And if I'm moving, when I'm moving, I have the ability to bump into other matter and move it. Okay?
Yeah, I thought that's it. Maybe it
So
was.
when I was, hold this thought. So when I was moving, I had the ability to move matter. This is matter. So that is an example of matter that is, or energy in motion. Make sense? And I did do that on purpose. My goodness, I'm not that cool.
I like you're coming from him. I see.
Never mind. Okay,
What about ghosts?
so types of mechanical energy that, or sorry, types of energy of motion that we'll talk about are mechanical. That's like me actually moving or windmills actually rotating. That's all mechanical and it can be converted into different forms. What's another word for electromagnetic energy? What do we usually think of this as?
Waves.
Waves.
Wait, I was right? Yes.
But I'm thinking light, right? Light is electromagnetic, as are like X-rays and so forth. So energy that travels as waves is electromagnetic. How about thermal? Good. Okay. Even if you have something that doesn't appear to be moving, the molecules within it are definitely moving, unless they're at absolute zero, which nothing can really get to that we know of. So everything has some level of thermal energy. What is it called when it has a lot of thermal energy? What phase is that going to be? Hot phase, which is the, you know, one of the three that all second graders learn. Solid, liquid, and hot. Gaseous. Biology, we don't have to worry about plasma.
I feel like we all should worry about it. It seems pretty dangerous.
Yo, plasma's extra hot.
So, yes, it is true. If you have enough thermal energy, you can make plasma where the atoms actually break apart. But let's just keep atoms together. If they're moving super fast, it's a gas. Slow them down, slow them way down. And what phase do you get when you've got the lowest amounts of energy there?
Solid or cold phase.
Which is also the chilly one. On the flip side, not all energy is actively moving. Sometimes it's just stored up and can be released for later.
The couch potato.
This is the one that we're going to mainly focus on, is that chemical energy is the most important type of stored energy when it comes to biology. Anytime you make a bond, there is some energy that is getting stored as chemical energy, and every time you break one, that energy is getting released. So we can see that there's this constant transfer of different types of energy. Okay? Theories. Remember when we talk theories, what do theories do? Theorize. Explain the why, right? Now we're going to look at laws. And laws just state what happened. And there are two really important laws that you need to know. The law of conservation of mass and energy. They basically say the same things. You can't make or destroy matter. You can't make or destroy energy in any chemical process. Listen to Einstein.
No.
So what these two laws are saying is that all the matter in the universe is stable. Whatever is existing will continue to exist. It can't be destroyed. Same for energy. The level of energy in the universe is consistent. It does not change. It moves from one form to another, but it does not increase or decrease.
So is that like part of the question on the prison?
Yes.
So I would have gotten that
I don't know. What'd you answer it?
wrong.
Okay. So let's look chemical reactions first. If we're saying that matter can't be created or destroyed, then that means whatever you start with, you have to end with. What are the chemicals that you start with in a reaction called? And the ones you end with are called?
Products. I do know that.
Okay. So when it comes, this is the piece that you probably got are the least familiar with, and or this is completely new, so make sure we're really thinking this through. Chemical reactions aren't just about the matter changing, because remember we talked that there's one really important type of stored energy, and that type of stored energy is chemical energy. It's the energy that is in the bonds. So if chemical reactions are all about changing the bonds, then that means we're changing the energy associated with those bonds too. For example, if I take fireworks and they get lit up and explode, some of the energy that was in the chemical bonds to begin with got released as what? Light, heat, sound, that loud crackle of the pop of the 4th of July fireworks. The heat. Yeah, that was a Rice Krispie reference, not a 4th of July. I'm fired. It's all good. So there's this constant switch between types of energy, and chemical reactions are really all about changing around bonds. That's going to affect the matter as well as the energy that are involved. So there are 2 rules that I want you to make sure to know. So the first idea here for any chemical reaction is for you to get it started, you have to break bonds. You have to make it so that the reactants are no longer stable. Because when they're not stable, they can react. They can join and form new combinations. And the only way to break those bonds is to add energy, maybe a ton of energy, maybe just a little bit of energy, but something needs to be added. They have to move enough that they break. So the first part of all chemical reactions is adding energies to break the bond, and then new bonds are going to form. When those new bonds form, that's going to release energy. Okay, we can kind of draw this like this, right after I drop my pen. Okay, here's the reaction. So the course of the reaction, start on the left, finish on the right. Here's the energy that is in the chemical bonds over here. I'm going to start with reactants and end with products. And I'm going to put them on the same plane for now, but we'll talk about when it can be different. For me to go from reactant to product is not a straight line. I have to add energy first, which means the energy overall has to increase and then has to decrease. Energy in, energy out. Are we okay with all of this so far? Okay. If we're okay with this, then we can start building on, making things a little bit more complex. So let's start, speaking of complexity, talking about what kind of chemicals have more or less energy in them. To do this, I want you to think about stability and I want you to think about complexity. Which of these sets of blocks has the highest amount of complexity?
Blue.
Blue. What did I have to do if this was something that I built? What did I have to do to make this stack of blue blocks?
It's a lot more work.
How physically walk me through? What happened?
Stack another blue.
I had to pick one up and
Put it
move
down.
it. I had to take matter and move it.
Pick it up and put it.
I pick things up and put them down. Okay? I'll edit that out. So picking stuff up, stuff, matter, moving stuff, moving matter, energy, it takes energy to physically build this structure. And the energy doesn't go anywhere, now it's just stored. By putting the blocks into a stack, I've stored extra energy in them. Now they have energy just by virtue of their position. They could fall and release that energy. Are we okay with that? And how about this guy? How much energy do you think the little singular red block has?
Not much at all.
Not much. But how stable is it?
Very.
Okay, if I came over and stomped my foot really hard right next to these blocks, which tower is the most likely to fall over?
Blue.
The blue one. So more complex means more energy, but less stability. Are we okay with all this? Smaller molecules, less energy, more stability. Well, why are we talking about all this? So one important type of chemical reaction that happens in your body is the type called anabolism, or anabolic chemical reactions. Like if you think of anabolic steroids, those are the ones that cause your body to build muscle. And all anabolic reactions are doing that. They're building something. So we're taking simple molecules and we're building them up. So we're adding in a ton of energy, and sure, we're getting a little bit of energy out, but where's the rest of it going? If matter and energy are constant and energy can't be created or destroyed, We're putting a ton of energy in, just a little comes out. Where's the rest of it now? It's in the bonds of the chemical that you've produced. So now this guy is nice and chock full of chemical energy. So by building up a molecule, which is an anabolic reaction, I've put energy in. Chemical reactions that have to get energy added in are called endergonic, okay? So an endergonic reaction is one where energy is absorbed over the course of the reaction. It goes into forming chemical energy. Okay, if you've learned endothermic, it's the same idea. In fact, endothermy and endergonic can almost be used interchangeably. So if you've taken AP Chem, or even, did they do it at all in regular Chem? Or was that AP?
I have AP.
Okay, so for those that have taken AP, same concept here, okay? So anabolic is all about building stuff up. On the flip side, see, like steroids. Thank you for, yeah, you came in late on that one. And on the flip side, when we take very complex molecules and break them down, that is going to be what is called a catabolic reaction. And I'm taking the energy that is stored in the bonds of my reactants and letting that energy go. These reactions, because energy gets released, are called exergonic or exothermic, and it just means that we're releasing the energy. So far, so good?
Yeah.
Okay. So the very first thing that needed to happen in this catabolic reaction, before I could get this reaction going, what had to happen? Did it just spontaneously ignite?
Yes.
What had to happen for me to be able to get the energy out?
Motion.
I needed to give it enough energy that I started to break the bonds of those complex carbohydrates. I needed to light it on fire. And the energy right here, we call this the energy needed to get the reaction started, is our activation energy. So the energy that I put in the first place, the lighter, is our activation energy. And when we put that energy in, it's enough to start breaking the bonds so that now we can release energy when new bonds of more simple molecules form. The problem is that in your body, that's probably not a good idea to light yourself on fire. Like, let me publicly, I'm on YouTube right now saying, do not light yourself on fire. You've all heard it. So, fire. So what do? Instead of using fire to meet this high activation energy threshold, we can use something called catalysts. And catalysts reduce the activation energy needed to get a reaction started. It lets it happen without having to light it on fire first. It lets it happen at lower temperatures. So this idea right here of catalysts, we're going to come back at the end of this unit and talk a lot about a particular type of catalyst called an enzyme. But what you should realize is that, notice here, the energy in the reactants doesn't change. The energy in the product doesn't change. The total amount of energy being released doesn't change. The only thing that changes is the amount of energy that I need to add to get the reaction going, my activation energy. Does that all make sense? So I know that